Swayam Prabha. Digital India. Educated India.
So let's continue with our excursion into recreational mathematics in some sense, various things in probability theory. Did you try how many people tried out the circle problem, the random chord problem? Let's take a random person. What answer did you get? So what's the answer that, what do people get? Anyone who answered the question, what do you get? Pardon me? 1/3. So he's got an answer 1/3. Anyone agrees with that? Any other answer? 1/2. Okay. 1/4. And they're all right. Every one of these answers is right actually. And you wonder why multiple answers are possible. To cut a long story short, it has to do with the fact that when you say something is random, you have to define what exactly is random and what is distributed in what manner. What's the probability distribution? So in the circle problem, to go over it quickly because I want to do many other things today, here's the center and you draw a chord. If the angle subtended by this chord, this angle theta, if that's less than 60 degrees, then clearly this chord is shorter than the radius. If it's 60 degrees, it's exactly equal to it, and it's more than 60 degrees, it's greater than the radius. So one would think that if you took a circle and marked a point on it at random, call it A, and drew a chord at random, and this point is B, what you've essentially done is to choose the 2 points on the circumference, the endpoints of the chord, randomly, uniformly distributed on the circumference of the sphere, of the circle. Then the probability here of this chord being less than the radius is given by the measure of this angle with respect to the 360-degree angle here, 2 pi here, and that's 1/6. So the answer would appear to be 1/6. But you see, you could have chosen B on the other side. So that too is permitted. So the answer is 1/3 because you've got a 120 sector which is permitted and a 240-degree sector which is outside the scope of your investigation, right? So the answer in this case, the probability is equal to 1/3. But I could equally well argue that if you give me a circle, I choose a point at random here and call it the midpoint of the chord. Choosing the midpoint of the chord uniquely specifies the chord completely. Then it's immediately clear that if you choose this along any radius, doesn't matter which radius it is, then all points which lie in the second half of this radius are going to subtend an angle which is greater. The chord is, if you're here, the chord is here for instance, that's less than the radius of the circle. And if it's in this other half, it's greater than. So the probability is a half because you have taken the midpoint of the chord to lie uniformly distributed on any given radius. But if you take the attitude that, look, even that is being too specific, I take the midpoint here to lie uniformly within the area of the circle, then all points which lie within a circle of half the radius here are going to be out because the chord is greater than the radius, and those which lie outside are going to be in. So in this way you get an answer which is 1/4. The allowed values are 1/4. This is called Bertrand's paradox. There's nothing paradoxical about it. It has to do with the fact that when I say the chord is drawn at random, it's not good enough. You have to tell me what property of the chord is distributed in what manner. If you tell me the midpoint of the chord is distributed uniformly inside the area of the circle, then the answer is one value. If you tell me it's uniformly distributed along the length of any given radius, it's another value. And if you tell me its endpoints of the chord are uniformly distributed on the circumference of the circle, that's yet another value, etc. So it simply has to do with defining randomness properly. Okay, so just saying something is random is not enough. So that's the answer to this question, and we'll now go on to something else, and I want to spend some time on it.
Say that midpoint of what is uniform distributed around radius of the circle. We explain how the probability comes out to be one half.
If it's in one half of the radius, then you get a chord which is longer, and if it's in the other half, you get a chord radius which is shorter.
But then the limiting case will occur when the midpoint of the chord is at a distance of root 3 r by 2. When we draw the diagram, when we draw the construct.
You can get several other values also, depending on what property is random. Okay, but most of them would be related to one of these three things. There are other ways of defining a random chord, which I'm not getting into here. My point was merely to illustrate that you have to say what's random, what is distributed in what manner. Okay, so let me now go on to a basic paradigm in random processes. This is called random walk. And it's the very essence of random processes, if you like. A large number of phenomena can be modeled by various kinds of random walks, and we will take the simplest of these in a manner which will illustrate the essential point involved here. And that's very easily demonstrated. In fact, instead of doing a random walk on a lattice, which is what I'm going to do a little later, let's phrase this problem in a more understandable fashion in the following way. I take steps at random. I take one step every second and I do it at random, completely at random in any direction whatsoever. After n seconds are over, I ask where do I end up on the average. On the average, my displacement as a vector would be the same point, would be 0, but the mean square displacement would not be 0. And now let's simplify this problem in the following way. Each step is assumed to be of the same length. That's an initial assumption which can be relaxed, and we will do so. But to start with, let's suppose each step has a uniform length, has the same length L. I start here, this is my starting point, origin, and then the next step is taken in any direction in space whatsoever. You can do it on a plane, on a line, 3 dimensions, 4 dimensions, etc. Let's take 3-dimensional space. So the next step is like that. This vector I call R1, this vector I call R2. And then I take a third step in any direction, R3. So you must remember that this whole thing starting to look like a chain polymer, long chain polymer, which is loosely hinged at wherever each monomer ends, completely free hinges. Any direction in space, and this goes like that, R4. R5, etc. And let's suppose you had it for going for a long time, and then you have Rn, the nth vector. This is the end point. This was the starting point, and this is the ending point. And the question I ask is, what is the distribution of this vector here? Which will obviously in general not have a length L, magnitude L, but what's the value of this distance here on the average? And what direction does it point on the average? Now, since we're not, it's intuitively obvious it can point in any direction in space. We'll not talk about that. We'll ask what's the distribution of the length of this vector here. So let me start by saying R, the sum vector at the end of n steps is R1 plus R2 plus Rn. Just a vector sum. Now I want the magnitude of this vector, so I take its square or dot product with itself. So therefore, Rn squared is equal to Rn dotted with Rn. And that's this vector dotted with itself. And each time each Ri dots with itself on the other side, you get L squared because it's just the square of the magnitude of each length here. And there are n of these terms, so it's n times L squared. Plus a summation from ij equal to 1 up to n and I not equal to j. These are the cross terms And the cross terms look like Ri dot Ri. Right? So over different realizations of this random walk, you're going to get different configurations here. But we want the average over all possible configurations. And for that we use this symbol, Rn squared. That's just this angular bracket. And the average of a sum is the sum of averages, as we know. So it's the average value of NL squared. What's that equal to? Little nn squared. There's nothing to average here. There's nothing random in this term. N is given to you. I tell you there are n steps that I take. And little l is given to you as a constant in the problem. Right? So it's the same for all realizations of the random walk. And there's nothing to average here. This term is different. This term is random. It's got randomness in it. So you have to put an average here. But any averaging is an arithmetic operation, just as an arithmetic mean of all the realizations, the answers in every realization. And this is a summation. Both are addition operations and they commute with each other. So the average value of this sum is the sum over the averages. Okay. That sort of thing doesn't always happen, but it does in this case, as you can convince yourselves. You should think about it a little bit. All right. And what's the average value here? Over all possible random walks, you have to take every vector step and take every other vector step, take the dot product of these two and take the average over all possibilities for either or both the steps. Well, the dot product of two vectors is the magnitude of the two vectors multiplied times the cosine of the angle between them. So let's suppose that you have some vector Ri in this direction and some vector Rj this direction with some angle theta ij between them. Then what's this term equal to? It's equal to the average value of the magnitude squared. What's the square of the magnitude? L squared. That's a constant. That L squared is a constant. So it comes out of the summation times the average value of cos theta ij. That's a random variable because in different realizations of the walk, theta ij would be different in general. And we want the average value of this cos theta ij. What should I do next? I have to put in some physical input here. There's no restriction on the theta ij's at all. The theta ij's can run from 0 to pi. The angle between two vectors can be either parallel or anti-parallel. Can all run 0 to pi. For every realization of this kind, there is another realization with equal probability in which this Ri, this vector pointed in the opposite direction. And the angle between the two vectors became this. That's pi minus theta ij. What's cos pi minus theta ij? Minus cos theta ij. So for every term cos theta ij, whatever the value of theta ij, I have another term with equal weight which is minus cos theta ij. And when you add the two, what do you get? 0. So it says that this angular average is actually 0. Every term in it is 0. Yeah. It's precisely because I'm choosing it arbitrarily with no bias towards any direction that this is possible. If it so turned out, in fact in real life, since I mentioned polymers as an example, I'm not talking about polymers here now, this is not going to happen because you see a long chain polymer looks like this. If you put it in a solvent, it's going to look like this. And if you magnify it and look at it as made up of monomers, it's going to look like this. But a real polymer has ligands on it which repel, and therefore you won't have self-intersections. The random walk will go like this, it will come here to intersect but then move away, it will come here to intersect but move away, etc. And that is a very non-trivial problem, because if you ask what's the configuration on the average in this sort of situation, this polymer remembers its entire past in some sense, all the previous steps in the walk. It can't go back to any path which it has already visited. That's called the self-avoiding random walk, and it's an extremely tough problem. To this day, many exact answers are known, but many others are not known about such walks. Okay. And it has practical implications in the polymer industry. Yeah.
Sir, if it was the mean of the cos square theta, then?
There's no cos squared.
Sorry, sir, if it was the mean of cos square, then how would we go on finding it?
Mean what?
Sir, if we had to find for some reason the mean of the cos square theta,
Yeah.
then how would we go about finding it?
You have to tell me the distribution of theta, and then I find the distribution of a function of theta.
Sir, from 0 to pi by 2. Sir.
Yeah.
Then how would we
Distribute
write
it how?
0 to pi by 2?
So the probability that the value is some theta is p of theta. That's the probability density that the value of theta is some given number theta, right? P of theta d theta is the probability that this angle lies between theta and theta plus d theta. And then you have the normalization, P of theta d theta integral from 0 to pi is equal to 1. So the total probability is 1. P of theta is the probability density. For continuous variables, you don't have probabilities, but you have probability densities, because you cannot resolve it to infinite accuracy. Given this, and now I tell you that it's uniformly distributed, every theta is equally likely, what's the value of P theta? It's a constant. What's the value of that constant? This condition has to be satisfied. And P theta is constant. So what's the value of the constant? Yeah, louder. Yeah, I heard that. 1 over pi. Yeah, that's all it is. It's 1 over pi. But in general, if you want cos squared theta or any function of theta, you want the average value. This is an integral 0 to pi d theta f of theta p of theta. That's the value of the average value. So if you want the average value of cos squared theta, where theta is uniformly distributed between 0 and pi, do 1 over pi integral 0 to pi cos squared theta d. Right? And what's that equal to? That's not the problem we are looking at here, but what's that equal to? How do you do such an integral? You write cos squared theta as? 1 plus? And then what?
Now we'll split the integral.
So what's the value?
1 by theta times theta with limit 0 to pi.
What's this going to give on integration? It's going to give sine 2 theta, right? And that will be 0, both at 0 and pi. So that's gone, you don't have to worry about it. This gives you a constant, pi. Okay?
Understood, sir.
If you give me some other non-trivial theta, this is a different problem. Then you have to put in that P of theta and integrate. Okay, coming back to our problem, we found out that Rn squared equal to n L squared. So we found that the mean squared distance from the starting point to the end point at the end of a random walk of n steps, taking one step every unit time, is nl squared. Therefore, the root mean square distance, RMS distance, is equal to square root of nl squared L times square root of n. N is the number of steps or number of segments.
What exactly does the RMS distance signify?
It gives a measure of how far away you are from the starting point. If you looked at it as a vector, on the average the vector would not move anywhere because there would be as many pointing in the opposite direction as in this direction, right? But the mean square displacement is not the same as the root, is not the same as the vector displacement. The mean square distance is not the same. So it tells you how far you are likely to be away from the origin. What's remarkable about that statement? This is just a constant. What's remarkable about it? What is the connotation we give to n in a random walk? N steps. And I said that you take one step per unit time. So what is it really telling us?
The
Amount of time you spend it. If you walked at constant speed and I walk in a line at constant speed like this, what is the distance I cover in time n proportional to? The time itself. Distance is proportional to the time, right? There's no root mean square, I'm walking in one direction and so on. But if you walk purposelessly, if you do this and you dither and you do this, then the distance you cover goes like the square root of the time. Another way of saying it is it takes you 4 times as long to get twice as far because you're drunk, right? The random walk is also called a drunkard's walk for this reason. This square root here, which looks very innocuous and very trivially derived here because there are n terms which are the dot product of each vector with itself was just n terms like this. This square root is the most important square root in the universe. It appears everywhere. And this sort of motion is called diffusive, as you'll see in a minute why I call it so. But this root is worth remembering. Okay. Now I take a step back and simplify this problem and do it in another context altogether. So let's do that and then we will get to where this n square root of n comes from. So now I'm going to do a simple random walk. The simplest random walk. And I'd like to relate this to what we already know, namely the binomial distribution. Yeah. What RMS distance? Root mean square distance? It's a measure of how far you are from the starting point. Yeah. So let's simplify this and say that I don't have 3-dimensional space. I'm going to walk in one direction, one dimension. I make life even simpler and say, just as I made time discrete by saying I take steps labeled by little n, I take steps of unit distance also. So I'm going to walk on a lattice. I'm going to walk on what's called a linear lattice. Goes on forever. And I have to label these sites, this long linear lattice, which is infinite in both directions. I have to label the sides of it. So let me label it with a label J and call this the origin O. On an infinite lattice, which is infinite in both directions, the origin is completely irrelevant. It's translationally invariant. No matter what point you choose, you can call that 0. Okay. This site I label as 1, 2, 3, all the way. This is -1, -2, -3, 4. The general site here, let me call it J. This guy is J -1. This guy is J plus 1. Now I play this game according to the following rule. I start at 0 at time 0 and time is labeled by n. It takes values 0, 1, 2, 3. Now I have a clock with me and every second I take a step. The step is exactly 1 unit long, so I go from one side to another. But I do this randomly. In other words, I have a coin, a fair coin to start with, could be an unfair coin, we can generalize easily. I toss the coin, if it comes up heads, I move to the right, if it comes up tails, I move to the left. That's all. And I play this game for time n. The question asked now is, what is the probability that I end up at some particular site at the end of time n? Okay? So I would like to know what is the probability, P, that I end up at some site j time n. Pardon me? No, after any finite amount of time n. So what's the random variable here? No, I give you n. I tell you at the end of time n, where am I? It's j. J is the random variable. And what's the sample space? What's the possible values of j? Minus infinity to infinity in integer steps. Okay. So what is Pj of n? What would your first guess be? First of all, there are some cases where Pj of n, j comma n is 0. I start at 0. I haven't put that down, but I'm assuming I start at 0. So if you like,
If j is greater than n, then the
Ah.
probability is
right, if j is bigger than n, you can't reach it in n steps. Even if you went continuously in the same direction, you can't reach it, right? But j can have both signs.
mod j.
So this is equal to, according to him, P of j comma n is equal to 0 if mod j is greater. Does everyone agree? You can't reach the place 10 steps distant in 9 seconds. So it's identically 0. It cuts off on both ends at n. Okay. When else is it 0? If I start at 0, can I reach the site 1 in an even number of steps? In 0 steps, I certainly can't. In 1 step, I can go here. In 2 steps, I have to go out of it. But I can come back in the 3rd step. Right? So what does it mean? Yeah, to go to an odd site, numbered site, I must have an odd number of steps. And to go an even site, I must have an even number of steps. So this is 0. Many ways of writing this, but 0 if n minus j is not even. N and j must both be even or both be odd. Okay. What else? And suppose these conditions are satisfied, j is less than, mod j is less than n and n minus j is even, then what is it equal to? How would I argue? This is exactly the coin tossing problem. In fact, the biased coin tossing problem, we put a bias on the random walk. But there's a dictionary, there's a translation between one and the other, which you have to figure out. So what would that be? Let's say I want to reach this site j. Okay? I'd like to reach this. I must have at least j steps. But I have a number n which is bigger than j number of steps, right? So it's clear that I could overshoot, I could undershoot, I could do whatever I like. So the number of steps to the right that I must take are steps. If j is positive, for instance, this must be equal to j at least plus the rest of the steps must cancel each other out in pairs. I must go forward, I must go backwards to cancel out, right? How many steps are left after I finish j steps? Out of n steps, I finish j. How many are left? N minus j. But n minus j must be an even number, right? And they must cancel out in pairs. So how many right steps do I need? I need n minus j over 2 right steps and n minus j over 2 left steps, right? Therefore, this is number of L steps. This is equal. It's n plus j over 2. How many left steps do I need? Is n minus j over 2. So the argument is to reach j in n steps where n is bigger than j in the same parity. I do n steps, j steps to the right in some order. I'm left with n minus j steps and they must cancel out in pairs between r's and l's. So the total number of right steps is n plus j over 2 and the number of left steps is n minus j over 2. I have to reach that point from this point. So this step, this is j steps. This is 0, this is j. I take those j steps. So what I'm doing in my walk is this. R, R, L, 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 R, L, R, R, L, R. And I'm done. Of these, the number of right steps must be at least j, and then I'm left with n minus j steps, and they must equal the number of L steps, whatever is left. So n minus j over 2 added to j gives me n plus j over 2 right steps, and n minus j over 2 left steps. So what's the factor here?
So essentially, if we had 10 turns and we needed to reach, for example, step number 4,
Right.
you were asking what is the probability that we will get 7 heads and 3 tails.
Yeah. Yeah, we'll come to that in a second. You'll see there's an exact mapping to that other problem. So you need 4 steps to the right, you're left with 6 more steps, and there must be 3 right, 3 left, in some order. Right? So if you had a biased walk in which the coin is biased, you need to move with probability p to the right and with probability q to the left. This will be exactly this. It will be what? P to the power n plus j over 2, q to the power n minus j over 2, right? Multiplied by the number of ways in which I can organize these steps. I can arrange the steps. And what's that equal to? NC what? Out of n steps, n plus j over 2 must be right steps. The number of ways of choosing n plus j over 2 right steps out of n steps. That's NC, n plus j over 2. You could have written this as NC n minus j over 2. It doesn't matter because NCR is the same as NC n minus r. What sort of distribution is that? The binomial distribution. What's our translation now between the random walk problem and the earlier coin tossing problem? The correspondence was n goes to n. The number of steps is the same as the total number of coins that we tossed. And the number of heads is n plus j over 2. The number of tails is okay. So take whatever you did there and translate it back into this using these symbols. So that's actually the solution to the one-dimensional simple random walk problem, even for a biased walk, because we've got these general factors here. What would happen to this factor if you had an unbiased walk? If you had a fair coin, P equal to Q equal to half, and then what would this become? 1 over 2 to the power n. 1 over 2 to the power n, right? So I want you to do the following. So what is the mean square displacement? J squared in n. It's intuitively clear that J itself would have an average value which is 0 for an unbiased walk. Because there is no bias to the left or right, the total displacement from the origin will actually be 0. Because for every walk with a displacement to the right, there is an equal walk with the displacement to the left. But if you square this J, that's not true. So you get a non-zero answer for the mean square displacement. And what is this equal to? It's a function of the number of steps. This is equal to a summation P of n comma j times j squared. Summation over j. What do you think this is going to be? Take a wild guess. Now what are you doing? You're taking steps like this. You're going way back and then you're going forward indecisively. Your mean displacement is 0, but the mean square displacement is not. How far do you think you'll get in time n? We just saw the earlier polymer problem in 3 dimensions. What answer did we get there? Root n. So I want you to show that this is equal to root n of t equal to. That's an exercise for you. Go back to the coin tossing problem. You know the generating function, put that in and find the mean square value of j. And show that's exactly equal to n. Therefore, what's the root mean square value of j? Square root of n. Square root of n. Okay. This is called diffusive motion. This is what diffusing particles do. So if you take a drop of ink and drop it into a beaker of water, and still water with no thermal currents, you'll see this ink putting out tendrils and moving aside and so on. The envelope of those tendrils will go increase like the square of the time, the square root of the time. And that appears here. Minus infinity to infinity, but most of the j's don't contribute because the p of n comma j vanishes for j greater than n. Gets cut off at plus n and minus n on both sides. So the summation, quite right here to point that out, although the summation over j runs from minus infinity to infinity, because p of n comma j is 0 if mod j is greater than n. So the series gets cut off. You just get binomial coefficients. So this has huge implications. You can generalize this to any number of dimensions. It's independent of space dimensionality. This square root is robust against anything. The steps could be in any direction in space, doesn't have to be in a lattice, could be in any dimensional lattice no matter what, or a continuum no matter what. The steps themselves, the successive steps need not have the same length. They could be distributed themselves in a probability distribution. We don't care. Under extremely general conditions, this square root remains robust. Very powerful statement. Now I want to approach the same problem from another angle altogether. We saw that the mean square distance went like the time. The root mean square distance went like the square root of time. We can ask, instead of doing this, I give you the distance and say what's the mean time it takes to reach that point. So let's do that problem and let's do it in a similar setting, and we should see whether we get an answer consistent with this or not. But that requires now assuming something about the process itself, assuming that it's what's called a Markov process, but we'll do this in simple steps. Let's make life a little easier by again coming back to this square lattice and doing the following, and this linear lattice and doing the following. Here's the lattice label 1, 2, etc. minus 1, minus 2. Again, I start at 0. I want to know what's the mean time it takes to travel a certain distance. And I want to compute this by calculating the mean time it takes to travel unit distance and to travel double the distance. So let's now start this problem, random walk off, by saying that I mark these two sides, minus 1 and 1. I mark this side here with a cross and this side here with a cross. And I have an unbiased walk, so the coin is fair. Otherwise, I drift to one side completely. I put it two crosses. I start at 0, and it's a very simple problem now. I toss a coin and move to the right with probability half, or probability minus half to the left. Probability half to the left. Okay. The walk ends if I hit 1 or 0, 1 or minus 1. There are traps at these 2 points. Okay. And I ask, what is the mean time it takes to start from the origin, which I will mark with t0, to reach plus or minus 1. This is the mean, already a mean over all possible random walks. What is the mean time it takes to do this? I take a time step at the end of 1 second. What's the mean time it takes to reach? It's just 1. There's nothing to average over. The first time I take a step, I'm done, I'm finished, right? So this is equal to 1. Now I change the problem and say, what's the mean time it takes to reach plus or minus 2? So I put the crosses here. Now this is a much harder problem. Much harder. Because you see, you have to average over all possible walks, and you could forever not hit 2 or plus 2. Because you could go from 0 to 1, 1 back to 0, 0 to minus 1, back here, this way. And finally you decide, okay, I jump and I hit this. So you have to do a summation over an infinite number of random walks with appropriate weights. What do you think? That looks an awfully hard problem, right? But the assumption that the steps of the walk are independent of each other, it's called the Markov assumption, that makes the walk problem very easy to solve in this case. And the answer goes like this. I want t0 plus minus 2 is equal to, every argument will be plus minus 2, so let me just call it t0 for simplicity in this fashion, is equal to, I start at 0, and the first step is either to the right to site 1 or to the left with site minus 1. What's the probability of reaching site plus 1 from 0? Half. So it's half multiplied by, once I am at 1, then I need the mean time to go from 1 to either 2 or minus 2, because it's independent of this half. So it's just multiplied by t1. Okay? But there's another possibility. I could have moved to the left in the beginning, and the probability for that is half t minus 1. The probability of reaching this or that starting at minus 1. Agreed? But now what's t1 equal to? If I'm here, I hit with probability half, I go to 0, and then I have to multiply by t0. So it is half times t0. And then what? Is this argument completely correct? I'm going to come back to this. I fooled you a little bit here, but we'll come back to it. What happens here? Plus half. And if I am already at that point, the time taken is 0, right? So half into 0, and we are done, we are finished. Tell me what was wrong with this statement, What I am doing is starting at 0, I toss a coin, it comes up heads, I move here. I want the mean time to go from 0 to plus minus 2. Right? At the end of the first step, I find myself at 1. But I've finished one step. But I've already finished one step. So time 1 has elapsed. Therefore, this term is not correct. But it's 1 plus t1. Because one time step is gone. This is time that we're measuring. Okay. Plus 1/2, 1 plus t minus 1. Similarly, if I'm at t1, I move back with probability half, but I finished one time step. So it's half into 1 plus t0 plus half into 1 plus t2. But t2 is 0. By symmetry, it's clear you get exactly the same equation for t minus 1. Because the problem is completely symmetric with respect to right and left. I don't even need to write that equation down. Will you permit me then to simplify by saying t minus 1 is the same as t1? Whether I start at 1 and go either to plus 1 or minus 1 is the same as starting at minus 1 and going to either plus 1 or minus 1, plus 2 or minus 2. By symmetry. So we have a set of equations which actually looks like you can solve it. What are these equations? Because this is t1, this is also t1, this whole thing becomes 1 plus t1. So t0 minus t1 is 1. And what's t1? What does the second equation tell you? Please solve for t0. You can solve for both t0 and t1, but solve for t0, which is what we are interested in.
Sir, we get 4.
You get 4. So it says that on the average, to go twice as far, to go to 1 or plus minus 1, it took unit time, but to go to plus minus 2, you take time 4. You can generalize this to arbitrary j there and minus j here. And starting at 0, you should show the answer is j squared. So while mean value of j squared in the random variable, random walk problem, the mean, if the j was a random variable, the mean value of j squared was equal to the time n. Here time is a random variable, the number of steps. To go distance j, you take time. What's the mean time taken? J squared. So the same square root. It's exactly the same square root. You can play this game with other things, you can put in other biases, you can put a boundary here at this point, etc. But the fact of the matter is this diffusive motion has the square root of j appearing all the time. Crucial point. But if you had walks which are a little more complicated, and try this problem out. It's again just writing a set of equations. I take a triangle, let's call the vertices 1, 2, 3. I'm going to do a random walk on this triangle here by taking steps from one side to the nearest neighbor sides, and I put traps at these 2 points. I start at 1 and I flip a coin. With probability half, I move along to 3, or with probability half, I move along to 2. with equal probabilities. What's the mean time it takes to go from 1 to either of the two traps? 1 at unit count. Now I do the following. This is called decorating the graph. I extend the graph's length, I scale by 2, I double it and put sites in the middle. Just as I traveled unit distance here, now I have distance 2 on this side. And there are traps at 4 and 6. From 1 with probability half, I move at the end of each time step to either 2 or 3. From site 2, I move with equal probabilities to every nearest neighbor site, with 1/4 probability to 1, 3, 5 and 4. Ditto for 3 and ditto for 5. Now the question asked is, starting at T1 to go to plus or minus 4, 6, to go to either 4, 6 equal to 1. The mean time to start at 1 and go twice as far to 4 or 6. What's that equal to? Again, a set of simultaneous equations, linear equations will follow, and then you have to calculate this distance. So that's your homework problem. Unbiased walk, equal probability to go to any nearest neighbors. Notice that in this problem, there is an obvious symmetry between 4 and 6. Every walk that you do like this, there's a counter walk on the other direction. That symmetry can be used. Okay. But many strange things happen with random walks. This is not, the answer is not going to be 4. Looks twice as far, but it's not 4. Because what you have is an example of what's called a fractal structure. In plain terms, there's a loop here in which you can get stuck for a long time. So it's actually a number bigger than 4. Happens to be an integer, but you can compute what it is. Okay. So a lot of strange things happen in the case of random walks. On a future occasion, I'll tell you a little more about it. But I'm going to leave you with a problem and then I'll stop. Okay. Again, we go back to our favorite toy, which is the linear lattice. Let me call this side 0, this is minus 1, minus 2, minus 3, etc. This is side 1, etc. I now do a random walk which is biased. So I have a coin which when comes up heads I move to the right, when tails it move to the left. But the probability of a head is P and the probability of a tail is Q. And Q is 1 minus P. So I have this coin. If it comes up heads with probability P, I move to the right. If it comes up tails, I move to the left. And this lattice goes all the way to minus infinity. That's very important. Unfortunately for me, there's a crocodile waiting at 1. And if I take a step to the right, I fall into the jaws of the crocodile. And I take a step to the right with probability little p. So I leave myself entirely to chance. I start at 0 and I ask the following question. What is the probability S of p that I don't die at all? I'm one step away from dying. One step to the right and I'm gone. So the question asked is, as a function of this bias parameter P, what's the probability that I can actually escape the crocodile forever? And you can intuitively see it's very important to have an infinite lattice on the left hand side. Because if you had a finite lattice here, you're sure to die. There's no question, because sooner or later you're going to move to the right and you're going to hit it. But if you have an infinite lattice on the left hand side, you might wander off to infinity. Okay. And you have to calculate the probability of survival S of p as a function of p. What is S of 1?
Q.
Probability of survival is 0. Because if P is 1, first step you toss a coin, you move to the right and you're finished. What is S of 0? If you move only to the left, you survive, that's for sure. The question is, what happens in between? In particular, if the coin is fair, what happens? What do you think will happen? Do you think you'll survive, or do you think that you'll not survive? Even though the coin is fair? That's the limiting case in between. So calculate this and I'll show you a trick. It's on the face of it looks like a difficult problem, but it's actually quite simple here. You must exploit the fact that this lattice is infinite. Okay. This is a non-trivial exercise. Think about it a little bit. It's an example of what's called a first passage time problem. And the question I'm asking is first passage from 0 to 1 a definite or sure event with probability 1 or less than 1? This is the question I'm asking. Okay. If the survival probability is less than 1, that means soon there are realizations where you're going to fall into the trap. The next question asked is what's the mean time it takes to fall into the trap? That would be of interest. And it turns out, and I'll give an answer, partial answer, if the coin is fair, you're sure to fall into the trap. But if the coin is fair, it also takes you an infinite amount of time on the average to fall into the trap. So here's a process which is a definite process, which is sure event. It's a sure event. Falling into the trap is a sure event. But the mean time to do so is infinite. There are technical terms for it and so on. So these are the sort of little subtleties that probability theory comes up with. But I'll show you a simple way of deriving the result here without any complicated algebra. So let me stop here today.